Good evening. Thanks for coming for the React meetup for this month. Tonight the hashtag is React London. My name is Xavier. I work at Red Badger as a software engineer. That's weird to hear myself. And so Red Badger is a digital consultancy company. We work in a cross-functional team, and we work on a lot of different projects. And one of the last projects we worked on, and we are really proud to work on it, was Pride. We worked on the React Native mobile application with them, so that's why you found this lovely bottle on your chairs. And we are always looking for new talent at Red Badger, so please come to talk to me or Laura and Becca if you're interested to know more about the different kind of position we have and different projects we're working on. Or you can send an email at jobs@redbadger.com. If you're interested to talk at this meetup, please send an email at hello@react.london. Any subject is always interesting, so please do. We do have a code of conduct if you're interested. You can go to meetup.react.london. And so yeah, tonight we have three speakers coming. We will have the two first presenting their presentation, and a break, and then the third one. So first, we will have Michele Bertoli from Facebook. And thank you, Facebook, for having us tonight. And he will talk to us about the setState machine. Thank you, Michele.
Does it work? Yeah, okay, perfect. Yeah, I'm Michele. I love React. I work upstairs, and I build user interfaces. And one thing that I learned in building user interfaces in my career is that state management is super hard. And as engineers, we have to keep track of all the state changes over time, and we have to make sure that the user only performs a subset of valid operations at any given point in time. And I was wondering if this complexity is intrinsic in building UI. There is nothing we can do about it. Or maybe we are using the wrong approach. And now I'm going to show you what I mean by wrong approach. I'm going to use the infinite scroll as an example. So we're going to build an infinite scroll component. I assume everyone has a rough idea how it works. My solution would be this. First of all, I would attach an event handler to the scroll. So every time the scroll fires, I'm notified about it. When I'm notified about this event, I just check if the user scrolled more than 90%. And if that's true, I fetch more data, and I append the data to the page. And this pretty simple solution. There are different ways, but just pay attention on the approach that we're going to take. Because if we were building a scroll component like this, this would be the core functionality of it. So we would calculate the scroll percentage, and if the scroll percentage is greater than 90%, then we would fetch more data. Done. Actually, it's not done, because we figure out straight away that we are fetching more than expected. In fact, the scroll event keeps on firing when we started already fetching. And this is when things get fun, because one solution is using a state flag. So we set a state flag is fetching to true when we start fetching, and then we just check for the flag when the scroll event happens, and if it's true, then we ignore the event. And this is a very common practice, but now the component is going to do two different things. One thing when it's fetching, and one thing when it's not fetching. And the same applies on the render method as well. You're going to have a ternary, for example, to show a loading indicator. And this works anyway. But what happens when there is no more data? When there is no more data, we want to detach the event handler. We want to start fetching, because we don't want to fetch unexisting pages. So we use another flag, has more. If there is no more data, then we detach the event handlers. And what about errors? Has error, another state flag. So now the component has a lot of different behaviors. And in this case, we show an error when there is an error. Otherwise, we render null. And this can go even worse. No blame on the author. I write code like this every single day. But this is taken from Redux, and the async example. And this is a nested ternaries of state flags. Like, this is pretty complex to read. And this approach is called the bottom-up approach. where you start solving a super simple problem, and then you keep on adding to it as soon as you find edge cases. And we start focusing on linear transition. Like, I'm sure things are going to happen like A, B, C, but that's not true. You very soon realize that you need context. So it's not about on this event perform this action. It's more like on this event perform this action only if it's not fetching, has no error, is retrying, and whatever more. And in the bottom-up approach generates code that is harder to understand. Just think about the nested ternaries. And also, even though you can look at all the state flags in this, like for example in the initial state, but then it's not enough, because state flags can be combined. It can generate unpredictable states that you couldn't even imagine. And that's why I spent quite a lot of time thinking about like experimenting with state machines that, as the name implies, they should be really good in managing state, if they would solve these issues. And just to go through the basic super quickly, the automata theory studies these abstract machines and the problem that they can solve, and they can recognize a language, so they're used for regular expression. There are so many types of machines. There are machines with an infinite number of states. The machine we are interested in is the deterministic finite automata, and it has some properties. So it can have only one state at a time, so no more like is fetching, is empty at the same time. That cannot be true. And also it's deterministic in a sense that given the current state and an input, it's always going to give the same next state, which is hopefully what we want to give our users as well. And it's pretty cool because you can define a state machine using these five elements. So Q is the number of the possible, is the set of the possible states. Sigma is the set of the possible inputs. Delta is the transition function. So given a state and an input, is going to give you the next state. Q0 initial state, F final state. So it's a pretty clean way to define a component. And also you can design them using these state transition diagrams. This is a state machine that starts from A, it goes to C, like with a couple of transitions. Cool, but what does this have to do with the user interface? So let's see a real world example. So suppose you were building a user interface for Prettier, which is a code formatter for JavaScript and other languages, and you were building a button that would toggle the semicolons option from Prettier. So you start in the semicolon state, you toggle it, it goes into no semicolons, you toggle it, it goes back to semicolons. And this is a pretty cool way to define UIs. However, it doesn't scale. Because as soon as you add a second option, for example, space versus tab, you have to create one state for each one of the combinations. So you're going to have semicolons space, semicolons and tabs, and so on and so forth. And if you were to add a third option, like single quotes versus double quotes, the number of states would explode. Luckily, there are state charts, which is something that has been defined in 1987 by David Harrell in this paper called A Visual Formalism for Complex Systems. And it's basically an extension of what we saw now. Basically, it aims to solve the problems that we saw. And I'm going to go through a couple of main features just to let you know, like understand why this is useful for building UIs. So the first one is clustering. So suppose you have a machine like this where you have the state A, and on the transition alpha, it goes to B. But on the input beta, it always goes to C. So you have two arrows with the same input and the same destination. And in this as example are just two, but suppose you have 1,000 of them. What you can do to optimize the graph is just wrapping the A and B into a compound state, and just say from this area of the graph, like on input beta, it goes to always to C. You can also zoom out a bit and give this compound state a name. So you can say from D on transition beta, it goes to C. And this means also that every single state can have a state machine inside it. The second feature is orthogonality, which allows you to have parallel states. So in this case, this machine can be in the state A and C at the same time. So all the machines are independent. And this would solve the issue with the semicolons, tabs versus space. Then you would have another machine for single quotes versus double quotes. And they are all valid at the same time. Guards. Guards are basically the conditions in the state chart word. So here you're saying that this machine is transitioning from A to B on the event only if the guard that you put into square brackets resolves to true. So if that guard is true, the transition happens. And still, you have still conditions, but you have conditions only on transitions. So you don't need to check whether the machine is loading, is fetching, or is ready, because the machine knows its state. It's just, you can guard the transition. For example, if the user scrolls more than 90%, then you can transition. And last thing is actions, and this is the most interesting part, is basically the output of the transitions, how the state chart tells you to do something. And an action is just a label that you put in the state chart, and this graph is going to say when the machine transition from A to B on the event, the output of the transition is going to be the action label that you put there after the forward slash. And you can have actions on entry and a state and on exiting a state. And we'll see an example very soon. So the workflow when you work with state chart is this one. You send an event to the state chart. The state chart analyzes all the transitions and it checks all the guards. And whether a transition needs to happen, it collects all the actions. The actions from exiting the current states, the actions on the transition level, the actions on entering the new states. And it gives you a bunch of actions that you have to perform. You have to do something about. To quote Luca, I met him on Twitter talking about state charts. He wrote a great article on using state chart with Redux. Check it out if you're interested. He has this great analogy. He says, a state chart is like a magic box. You tell it what happens, so you send an event, and it tells you what to do. It sends back an action, which is just a label that describes what should actually happen. But now it's time to see some code. So the first thing we need to do is to install xState, which is an awesome library to build a finite state machine and state charts with JavaScript. It's also functional and stateless. Sorry. And we are going to build this machine, the pretty machine. Which is the one we saw before, but now we have actions as well. So now actions should be a little bit clearer. So we're going to send the machine the toggle event, so it can go from one state to another. And the machine is going to give us back these actions. So when it enters the semi state, it's going to tell us add semicolons. But it doesn't do anything. It's just a label of the action that we have to take. And when it goes into no semi, it's going to tell us remove semicolons. And the first thing we need to do is to describe the machine in a way that JavaScript can understand it. So we basically use a JSON object where we define the machine. We set an initial state, all the different states, so semi and a semicolon, and we pass it to the machine function from xState. The semicolon state will look like this. On toggle, it goes to no semi, and the on entry action is going to be add semicolons. As you can see, it's all strings, like no function. Like it's up to you to do something. The no semicolon state similarly goes to semi, and you have to remove semicolons when you enter it. So now, we have this pretty machine. We can do pretty machine.transition, and we can pass the initial state semi and the toggle event, the event that we want to happen. And this is going to give us back an object. And this object has a property called actions, which is going to be an array of action. In this case, is remove semicolons. So if you had semicolons and you just toggle it, you have to remove semicolons. But at this point, nothing is happening. It's just you get back an array. So how to use it with React? I built this library called React Automata, which is a layer on top of xState, and it adds basically state machine functionalities to React components. And we're going to build something cooler. Like we go back to the infinite scroll example. And the first state is going to be the start state, where the entry action is going to be attach, where we want to attach the event listener and start listening. When we're ready, the first thing we need to do is to fetching, because we want to fetch the first page. If the fetch succeeds, if we have more data, you see there is success and there is has more into the square brackets. If there is more data, we go to the listening state, where we keep on listening to the scroll event. And when the user scrolls, if the scroll percentage is greater than 90%, we go back to fetching, where we fetch another page, and this keeps on happening until we have no more page. And in that case, we go back to we go down to the finish state, where we detach the event handler. And this is a pretty cool representation of functionality of a component, I think. So yeah, if there is an error, I always know the handle errors. So we define this machine in the xState format, and we pass it together with the component to the with state chart higher order component that we receive from React Automata. But let's see how it actually works. So the first thing we want to do is to react to this attach action. So we said on the start state, the entry action is going to be attached. So how do we do something? We just define a method with the same name of the action in the component, and React Automata is going to fire this method at the right moment in time. And in this case, for example, we use the ref to the element to attach a scroll handler. When we are listening, we want to tell the state machines that we are now ready. And so how do we do that? We use the transition function that we receive from the props, from the higher order component, that tells the machine, okay, we're now ready. The machine is going to transition to the fetching state. And the entry action is going to be fetch. And fetch is an asynchronous call, suppose a call to the API, that can either go success, and depending on if there is more data or not, it's going to go in a different state, or it can give us an error. And how do we implement this? We define another method with the same name of the action again. And this is going to be fired at the right moment in time. And it would look like this. You extract the transition from the props. You use the load data. Suppose it's a wrapper on top of your APIs that returns a promise. When the promise resolves, we transition passing the success label, which is the success event. And as you can see here, we pass the data to the state charts. It's not us checking whether there is more data or not, because there are no ifs in my code. All the conditions are in the state chart. The state chart knows how to evaluate the condition and decide, depending on that, like whether it should go into a new state or stay in the current one. If there is an error, we transition to error. So the workflow, when you work with state machines and React Automata, it's even simpler. So you send the transition with event and some data. React Automata uses xState under the hood to calculate the next state, and xState is going to give back an array of action, and React Automata is going to fire all the methods in the component that have this action name. The second parameter of the with state chart higher order component is options. And if you set DevTools to true, you can connect your state machines to the Redux DevTools extension. So you can have the super cool debugging functionalities like time traveling, for example, because it's pretty similar to Redux in a way that the state changes over time. And there is also this component called action, where you can say, I want to show the children of this component only when the fetch action is fired. It's basically a conditional component that makes the render method maybe, hopefully, a little bit cleaner. But I'm quoting myself because I strongly believe in this. The best testing strategy is not writing tests. I don't mean that you shouldn't have your code base tested, because I'm really into testing. I love testing. I mean that whenever you can have tests for free, then you should go for it. And when I heard about state machines for the first time, I thought, if all the states are well known in the beginning and even all the actions are well known, then tests can be automatically generated. And in fact, this is what the test state chart functions from React Automata does. So you pass a state chart and some optional fixtures and a component. And this function is going to calculate all the paths from the initial state to all the other states. It's going to move the component to all of these states, and it's going to take a snapshot for each one of these. And this is pretty cool. Actually, snapshots are a functionality provided by Jest, which is a test framework for JavaScript. And snapshots look like this. It's basically the output of the render, like in a human-readable way. So when the machine is in a fetching state, the output can be something like this, like a spinner. When the machine is in the error state, you're going to see an error, like something went wrong. And so you're going to get a bunch of snapshots for free, and that's why you didn't write any test. You just write like one line, but that's fine, I guess. And you have all the components tested in all the states that it can have. Cool, so what are the benefits of working with state machine? The first one is you're going to have fewer bugs. And it's not me saying, because you wouldn't believe me, but it's written in a book by Ian Horrocks. He made an experiment, and he found out that his application had 80% less bugs when using state charts. It's easy to understand, because it's a visual representation, so you can share it with anyone in your team, not just engineers. Actually, designers are already using state charts when they design the user flow. And you are basically separating what happens, which are all the methods that you define in your components, to when it happens. When it happens is the state chart deciding it. You don't care about it. Max Stoiber, the creator of style components as well as Spectrum Chat, he played around with React Automata and state charts, and he made a prediction. Everybody's gonna start using state machines for UI this year. I'm doing my best. We'll see what happens. If you want to see an example, I built a calculator at this nice URL here. A calculator is usually an application that needs a lot of ifs, because you want to know if the user is entering the first operand, the second operand, a number before the decimal point or after. I built a calculator without any if, only conditions in the state chart. So the code is pretty clean and only basically reacts to actions from the state chart. Check it out. Takeaways. Think about states more than transitions. So if you use Redux, for example, you usually think about the actions that mutate your state. While with state machine, you think about all the different states that your reducers can give you. So you have more control. And then you connect them with transitions. Even though I'm not using state charts on a daily basis yet, I changed my approach. So instead of having a bottom-up approach where I build up stuff as soon as I find edge cases, I try to think about all the problems first. Obviously, I'm not going to lie, this requires more time, like before writing code. But then you can, when you have a state chart design, you can literally switch off your brain and just write code. And also read more papers from the 80s, 70s, because they tell the truth. This is the reference to the paper and to the book as well. These are like great. They inspired, obviously, my talk. Yeah, state charts dash paper and book. Last thing, follow these people. They inspired my talk as well. Fede introduced me to state machine. David is the author of XState, and also he gives great talk about this topic. Ryan is the author of React Router. He played around with XState and React for the first time. He recorded a video that was really awesome. And Eric is building in like documentation around state charts. So statecharts.github.io. Check it out if you are interested. It's very like comprehensive documentation around that. And that's it. I hope this was useful. If you wanted to ask me a question, I think we have a Q&A now, but also please come to me later when I have a beer in my hand as well. Thank you very much.
Thank you. Thank you very much, Michele. So who wants to ask a question? Here you go.
Hi. How are you doing? Excellent. Great talk. Have you tried implementing a similar state machine using Reason React's reducer components? And did you, if you have, find it take away a lot of the pain?
Yeah, I didn't write it myself, but I found out an example using Reason and the pattern matching that makes writing a state machine with the different state and transition way easier.
Because I was looking at the sort of like possible pattern matching outcomes of these things, like, oh my god, it'll be so clean if I can make it.
Yeah.
If you haven't done it, I might do it and see where it gets me.
That would be awesome. That would be awesome.
All right, great.
Thank
Thanks.
you.
Any other questions? It was very clear.
You can ask me any questions later. I'll be happy to talk about React and state charts and everything. Yeah. Enjoy the other talks, I guess.
Yes, thank you very much. So our next speaker is Sonya, and she's going to talk about security. So thank you, Sonya.
Okay, hi everyone, and welcome to Keep Calm and Fasten Your Seatbelts. So I'm Sonya, I'm a full stack developer. I'm also working as an AppSec engineer. As you can tell, I'm wearing a dark hoodie. I was in South Korea before coming to London. I was working as a business consultant, and I moved to the tech industry 5 years ago. Here's the little picture. You can find me on the social with the handle Sonya Moisset, the global unicorn. So let's start by defining what is cybersecurity and why is it important. So cybersecurity is meant to protect your online intellectual property from any form of cyber attacks damage or unauthorized access. Let's have an example, actually, of cyber attack. You might remember last year the WannaCry ransom crypto worm, which actually targeted computers running the Microsoft Windows operating systems by encrypting the data and demanding ransom payments in Bitcoin cryptocurrency. So Microsoft has released patches, but obviously some person didn't actually patches or updated their machine, so that's why what happened. At that time, just to give you an example, I was in France and my friend was about to buy a car, so went to the car dealer Renault, and they couldn't actually access the profile because of the ransomware. So it was actually true. It's not only in the movie, it's like it's really happening. So as a developer, we're actually more concerned about one part of cybersecurity, which is web application security. So we have a great definition from Wikipedia. Web app security is a branch of InfoSec that deals specifically with security of websites, web apps, and web services. So who here knows about OWASPs? Just a quick survey. Oh, nice. We have a few people. Nice. So as a developer, usually I don't really know where to start for security, and actually OWASP is a good starting point. So it stands for Open Web App Security Project. It has been created in 2001. And it's usually to give guidelines to developers. So what they provide AppSec tools and standards, complete books on app security, testing, secure code review, all of this, a lot of checklists on many common topics. And if you're interested, there's also a local chapter in London. So the first thing that would be good to check is the OWASP Top 10, which gather actually the most critical web app security risks. Usually OWASP releases this report every 3 to 4 years. The last is from last year. But I would say don't stop at only the top 10. There's obviously a lot more critical issues than that. They're constantly changing. So what are application security risks? So usually you don't have a little cute attacker on the side. It's usually a bad guy that wants to attack your app. So usually they will try different kind of attacks, like cross-site scriptings, SQL injection, trying to bypass security misconfigurations. And they will try to target security weaknesses in your app. And they will try to get control of or access to your assets. And ultimately, at the end of the day, they will actually try to impact your business, which means it could affect your reputation or image in case of a breach of data. So what changed from 2013 to 2017? So you could see on this one that there's a little bit of shifts in the top 10. So the injection is still the first one. We can find less vulnerabilities in the SQL database, but the NoSQL DB has still some vulnerabilities. Usually frameworks are quite secure by design. React is quite secure by design. I have to say this because here it's so yeah, there's less vulnerabilities, but cross-site scripting is still there, A7. We'll be talking about A9 actually in this talk. One of also the most common is broken authentication and broken access control, which means that usually when you play with the user ID in the URL, you can have access to another user or ultimately the admin. Also insufficient login and monitoring is a good one. So A9 is the using components with known vulnerabilities. So the exploitability is usually medium because you need to be a little bit skilled to craft a custom exploit. The detectability could be quite easy with some tools that I'm going to introduce you later on. The impact is actually quite random, but it could be high actually, and I have a couple of examples also to share with you. So how do you know when your application is vulnerable? So if you don't know the version of all your components you're using, and actually I can pick any of you and ask you, what's the version of React, what's the version of Redux, what's the version of Node.js, and probably you won't know all the versions of all the packages that you're using. If the software is vulnerable, unsupported, or out of date, if you don't scan for vulnerabilities regularly, or if you don't subscribe to security built-ins, so those can be, the application could be vulnerable. Also, if you don't fix them or upgrade or patch frameworks and dependencies, if the software developer don't test the compatibility of updated, upgraded, or patched libraries, so this is all application vulnerable. But as you would ask, how to prevent this? Usually, You could remove unused dependencies, unnecessary features, components, files, and documentation, which is quite good because you do a cleanup in your code base. You could continuously inventory the version of both client and server-side components. Also, you can monitor sources like CVE. So CVE stands for Common Vulnerabilities and Exposures. Some tools that I'm going to talk about are actually checking their packages through the CVE. You could also obtain components from official sources over secure links. For example, if you do npm add or yarn add, try to not do typo. Like, for example, if you do yarn add react, well, it can happen that you have a typo and do type react with 2e, and probably that other package has vulnerabilities. Prefer SIGN packages to reduce the chance of including modifier or malicious components. And also monitor for libraries and components that they can be unmaintained because in like 2 or 3 years they're not maintained, so don't try to download those packages. So every organization must ensure that there is an ongoing plan for monitoring, triaging, and applying updates or configuration changes for the lifetime of the app or your portfolio. So one example of a tool could be the GitHub dependency graph. It's an easy tool actually to set up because by default it's set up on all the public repo. If you want to set up on your on a private repo, so you have to go to the Inside tab, click on the dependency graph, and just allow the access. This is available for JavaScript and Ruby, which means that you need to have a gem file or a package.json. And it's a read-only, which means that GitHub will go through your package.json and just check if there's any vulnerability. Usually, if there's any vulnerability, you will have this yellow box saying that you need to check and patch your packages. So what I would recommend is enable your dependency graph on GitHub is really a quick fix. Set the notification preferences so you can have the alerting. Every week you will have a weekly digest of GitHub saying those repo have packages that are vulnerable. Another tool, actually, because probably you're not coding only in JavaScript or Ruby, and if you're interested to do the same for other languages, you could use Snyk. So it's basically doing the same and scanning all your packages and telling you if there's any vulnerable packages. Also good to know the NPM 6, which is in beta version, is also doing the same. So every user of the NPM registry will receive automatic warnings if you use code with a known security issue. You can also run the command npm audit, and they will also trigger any warning if you have any packages that are vulnerable. So now on to a real life example. Do you know what this script is? So actually this script was taken from Trump website. So the web developer find it clever to embed this script coming from Igor Escobar. I'm sure he's a great developer, but still it's a little bit dangerous to embed others' code in the website. So what was the problem, actually? So what could you do if you could modify that script and cause your own arbitrary JavaScript to execute on Trump's website? I know you can go crazy because it's Trump's website, but still, almost anything. So as a developer, you could modify the DOM, redirect the user, load in external content, challenge visitor to actually install software, add a keylogger and get all the password and credentials, grab any non-HTTP only cookies. So a lot of things actually you could do with this. Another example is the crypto miner case. So what happened here, I don't know if you heard about that one. So basically some UK and US governmental website have been used to mine cryptocurrency. So as you could see, this coinhive.com. So this script actually is an accessibility tool. So kudos for them for using accessibility for their website. But actually that company has been hacked, and this snippet of code has been embedded within the script. And if you can see, it's just starting mining a cryptocurrency miner. That snippet of code was obfuscated within the script. So basically what happened, someone managed to gain access to the storage where the file was. And the file, the accessibility one, is distributed from the CDN. So at the end now, every single website embedding it has a crypto miner It's cool for the guy who actually put this, got a lot of money from it. So how to protect ourselves from the second case, the crypto mining? We could use a super source integrity. Probably you might be familiar with the second bit with the integrity one. If you're using scripts from like Bootstrap or through CDN, you have this SHA-256 integrity checksum with the scripts. Some of you are now saying, oh, that what is actually, I was probably getting rid of it because I didn't see the use of having integrity. But it's actually pretty useful. So imagine if an attacker crafted a script and managed to embed it into Bootstrap or jQuery, the amount of damage that actually it could do with just a little script. So this website allows you to generate a hash that you can append to your script. So if the libraries modify upstream, the SHA-256 hash of the file, if it's different, actually the browser won't load, it will block it. It's a new W3C specification. And so the good news is the latest Firefox and Chrome are fully supported. The bad news is IE and Safari doesn't support it yet. You can double check which browser is supporting it on caniuse.com. Also, what could you, for the content security policy is a good solution for the first case, actually the Trump website script, where you could actually cherry pick a list of files allowed on your website page by page, and if it's not recognized in the browser, we'd actually block it. So it's an added layer of security that will help you block attacks like cross-site scripting or data injection attacks. So to enable CSP, you have two ways. Either you set your HTTP header, or you set it with the meta tag. I wanted also to introduce you to this cute whale. No, actually to Sonar Whale, which is linter made by Microsoft Edge team, which is a linting tool for the web. So I scanned the React website. I'm sorry. So I tried with the React website. The thing is, what we need to keep in mind when we're scanning web app with those kind of website, you know, those kind of website are giving you grades like A, B, C, and then you feel bad because you want to reach A because you have a C or those kind of things. Don't be too grumpy about the grade you'll get. The most important thing is to understand the need of your app, if it's really necessary to implement progressive web app, or what are your objectives in terms of performance, or if it's really a case by case. So what I would recommend that one is actually, usually when those you have those websites with letters, they don't really give you explanation what you need to upgrade to that kind of header or those kind of things. But if you click actually on those documentation, it's well documented, and they really give you why is it important, why you need to implement this on your website. So what's next? I would say after listening all that, and you might have some interest in security, but you don't necessarily want to work in security, what I would recommend you is to have a chat with your security team and propose yourself as a security champions. So usually the role of a security champion has to be defined by your organization, obviously, but usually it acts as a bridge between both teams and facilitate communication, because the security champion, at the end of the day, is the developer, so it's the person who has a better understanding of the code base. But also, you could receive a security training by being a security champion. It's quite good because during the Scrum ceremonies, you can act like the bridge between both teams. So to conclude, security is not the bad guy. At the end of the day, we're all working for the same products, and we all want the same outcome. The JavaScript ecosystem is amazing, but it can be dangerous some time to time. So I'll show you some example. But the good news is we have tools to help us prevent those threats. So try using them. It's quite simple to set up also. And I have to do this because my team is here. Get secure, be secure, and stay secure. Thank you.
Thank you very much, Sonia. Any questions from you? Ah, okay.
I didn't scare everyone.
What were the 18 security errors on the, I think it was 18, on React?
sorry, are you working?
36.
Yeah, are you working for a React website? I'm not sure. I can't remember. I think it was I'm not sure if I can. I think it was the content security policy and the sub-resource integrity. Usually they flag this because it's the latest actually feature. So yeah, they've been flagging. I'm sorry, React. Don't shoot me.
Any other question? Okay, but thank you very much, Sonya.
Thank you.
We're going to have a 10-minute break, so you can go back and have some more pizza and beer and everything you want. So I hope you had a nice break. So we will go after, if you want, we all go to the pub, which is the Marquis of Granby. Yeah, it's a weird name, like all the pubs. And so now we are going to listen to Bill talking about Webpack. Thank you, Bill.
Hello, everyone. Today we are going to be talking about the Webpack implementation. A little bit about me. My name is Bill. I work on the platform team at Improbable. We build web services that power this thing called Spatial OS, which is a platform for distributed multiplayer games. And we also build browser-based debugging tools for MMOs. And there's a couple places on here that you can find me online. In this talk, we're going to be digging into the Webpack implementation. We're going to be peeling back layers of Webpack, starting from a really coarse view of its interface and digging down really deep until eventually our goal is to understand how hot module reloading is implemented at a really low level. And if you want to refer to these slides later, there's a link here, and in the speaker notes, I've put in links to the Webpack source code in case you want to use this to explore the source. So the first question we need to ask is what Webpack actually is. So we want to start by looking at Webpack as kind of a black box. First understand Webpack's black box interface, and then go from there. When I first started using Webpack, I was just using it like a black box, and the Webpack team have done a lot of work to make Webpack very usable as a black box. But the problem with treating Webpack like a black box is that as soon as anything goes wrong, or as soon as you need to implement any kind of custom functionality, it's really difficult to work with. So I went on this journey into the Webpack source code, and you all are going to come along with me and learn all the same things. So this is the black box interface for Webpack. We start out with some browser-based software, and we can think of our browser-based software as a module graph, where each of our modules is some kind of source code. Maybe it's JavaScript, maybe it's compiled to JavaScript like TypeScript. We can also have things like images and JSON. And we feed this graph of source code into Webpack, and somehow, magically, it spits out an executable binary JavaScript file. If we've targeted Node.js, we can run this file directly, or maybe we want to embed it in an HTML file to execute in the browser. But this isn't a very fine representation because we don't know what's happening in between, and it's hard to tell where hot module reloading would fit into this model. So we peel back our first layer here, and what we can realize just from our intuition about working with Webpack configs is that we start with a bunch of source files. Usually we would call these entry points in our Webpack config, and we pass them into Webpack, and they undergo some transformations from these things called loaders. We can specify loaders for different file types, and eventually we're going to be producing this module graph of JavaScript modules. And this graph of JavaScript modules is going to parallel the graph of our source code. And each of these modules is going to be ES5, and the modules are going to reference their dependencies using the require function. And finally, once we have our module graph, of JavaScript modules, we're going to chunk them up. We're going to traverse that module graph, break it up into a series of logical pieces, and finally turn those pieces into files that we can execute in Node.js or the browser. And at this point, we're still thinking about Webpack as a module bundler, which is the terminology that Webpack uses on its website. But this terminology is a little bit arcane, and it would be more helpful if we could think about Webpack in the broader context of software build systems. So let's look at another build system that has the exact same interface as Webpack, modulo a few small differences. GCC. GCC takes a bunch of source files. They also have a module graph. We feed these into the compilation component of GCC, and out comes an intermediate representation of our source that GCC calls object files. These object files are partially assembled. There is some executable code in the object files, but any references to external dependencies are still going to be unresolved. So at the stage of compilation where we've produced object files, we still need to combine them together in some way so that we've got something that's runnable by our operating system environment. And the process of combining all of these object files together is called linking. And in GCC, it would be at this stage that we include our dependencies. And finally, after we've linked all of our object files, we can emit some kind of asset, a runnable binary that's targeting whatever platform we're interested in. There's a few other stages that happen in here. The first one is pre-processing. It happens before compilation. And in pre-processing, we're going to consider each source file on its own, and we're going to be treating it mostly as text. In GCC, we just do macro expansion on the source file without worrying very much about the syntax. And once we're linking our files, and once we have our intermediate representation, we're going to do two further passes over that intermediate representation module graph. The first is called optimization. During this phase, we're going to be traversing our intermediate representation and looking for ways to improve it, like by removing code that's shared between our objects. And finally, we have our code generation phase. This is where we actually write our code to disk, or in the case of Webpack, this is where we would set up a build of something like the Webpack dev server. So in Webpack, we can just swap out a few terms, and we have the exact same pipeline. Our compilation phase is just our loaders. Our linking phase is just chunking and also our asset emission. And we can think about Webpack as a compiler system without any issues. So let's start diving into the implementation of each of these phases. We want to be answering the question, what does a compiler system do? We don't just want to think about Webpack. We want to know in general what each of these phases is going to accomplish. The first phase we want to look at is compilation. This is where we're going to consider each source file on its own, and we're going to see how it becomes that intermediate representation. So we're starting with this module graph of source files, and there's all different types of source files, and somehow we need to end up with this parallel graph, but each of the source files needs to now be a JavaScript file. So this is what we want to end up with. Let's see how we can get there. The compilation phase of Webpack is a recursive process. So we start off with an entry point that we get from our Webpack config file. And we begin our recursive process by considering the entry point to our application. We consider this dependency. We apply all of our loaders to it. We're going to get deeper into those loaders in a minute. And once we've passed our source code through all of the loaders, we end up with a JavaScript module. The final loader needs to produce a JavaScript module. And once we've got our JavaScript module, we parse it. And we're still not considering any other dependencies at this point. We're just considering this dependency on its own. So we're going to scan through our parsed JavaScript module, and we're going to be looking for any references to dependencies. A reference to a dependency is something like a require call or an import function call to do lazy loading. And for each of these dependencies that we find, we're going to recurse over them as well. And we're going to continue this process considering each module on its own until we've processed every module in our graph of source code. And when we're done, we're going to end up with our parallel module graph that has the same dependency relationships as our source code, but each module is now a JavaScript file. So one of the most important parts of this is the loaders. This is where the actually interesting compilation happens. So let's look at how the loaders work. Like I said, this is where the actual compilation occurs. If you look on the right-hand side here, we specify a series of loaders, and whenever we're able to match one of these loaders to one of our source files, we execute all of the loaders specified. We run them from the last loader specified to the first loader specified. So you can think of this as function composition, where the last loader specified is past the source of the module, and the final loader specified needs to produce our JavaScript module. So it's like middleware. Each one of these loaders has an opportunity to do some kind of transformation of the source. We can implement pre-processing in a loader. We can implement any kind of compilation we want, as long as that final loader produces a JavaScript module. Once we've got our intermediate representation, we've got this module graph of JavaScript modules, we're ready to start analyzing it to eventually produce our executable assets, and this is the linking phase. We're starting with our intermediate representation. We have an entry point, and we're going to do a few passes over this module graph, making changes to it at a time until eventually we end up with something executable. The first phase is called chunking. This is where we traverse the graph and look for so-called split points, where we know we can safely break up this module graph to produce different executable files. And the second phase is called rendering, and this is where we traverse the chunks that we've identified to actually produce our runnable assets. So the first chunk phase begins with our intermediate representation. We traverse our intermediate representation, and we're looking for split points. And a split point is simply an asynchronous load of a module. So in this case, it's going to be an import function call. And when we find one of these lazy load calls, Webpack is going to know that it needs to start creating a new chunk from this split point. So when we find a split point, we begin traversing the module graph of that chunk, and we continue this process until we've identified all of the split points and traversed all of the modules in the split points. You might be wondering, what happens if we've produced some subgraph that has a bunch of modules, and then we try to asynchronously load one of those modules from within the same chunk? Well, Webpack is keeping track of all of the modules in a chunk. So when we realize this case, we're actually not going to start traversing the module graph again, and we're going to know that we can not create a new chunk. And once we've identified all the chunks, we now enter into an optional phase called chunk optimization. And you can enable this phase using the split chunks option. It's documented in the speaker notes. And during this phase, we're going to be traversing our chunk graph. And we're going to be looking for dependencies that different modules have in common. And when we find dependencies shared by multiple chunks, we're going to add those modules to a new chunk. And we're going to continue this process until we've identified all of the modules in common with the different chunks, and then we're going to record the relationship between the chunks. So we actually establish a dependency relationship between chunks in this phase. So in this case, the bottom chunk would know that it depends on the middle chunk in order to load. Once we've got our chunks, we're ready to generate source files from them. In this process, we start with the chunks, and we wrap our chunks in this thing called the Webpack runtime. Depending on the type of the chunk, this is going to be different. For a chunk with an entry point, we're going to wrap this in this thing called the Webpack bootstrap that loads up our entry point and passes in the data needed for the modules to reference one another. And we're also going to inline the module source in this type of chunk. And once we've wrapped all of our chunks in this runtime, we are going to generate the source for them. And we're also going to generate something called the manifest, which contains the hash of the module ID, and a function that's able to render the source. And we're going to use this manifest when we are checking whether a chunk has been updated, and we're going to use this manifest to know if we need to load new modules. You might be wondering, what is a chunk when it's been written to disk or when it's been sent over the wire? There's two formats for chunks. The first is an immediately invoked function expression, or an IFI. This is what we use when a chunk has an entry point. And the function is the Webpack bootstrap, and we pass in the actual module source to this function. And there's another chunk format called JSONP, where we basically wrap up our module source in an array, but we don't actually execute any of the modules. We just put them in shared memory. So let's look at the Webpack runtime. When we've produced our intermediate representation, we still need some way for these modules to reference one another, because if we simply concatenated all of them together, they wouldn't know how to talk, the modules wouldn't know how to talk to each other. So for a single chunk, we have an entry point, and our chunk is a big function. The body of the function is the Webpack bootstrap. It sets up a require function so the modules can reference one another, and it also sets up the definition of our module object so that our chunks can export different values to be shared with one another. It also sets up asynchronous loading of dependent chunks like we saw in the chunk optimization example. And finally, it loads the entry point of the chunk if the chunk has an entry point and it's loaded all of its dependencies. And when we load up our entry point, we're going to pass it that require function. And when that chunk needs to load additional chunks, it's going to use the supplied require function to load those other chunks. And then subsequent chunks are also passed the same require function, and they're able to reference one another. And if you're not familiar with what an immediately invoked function expression is, it's just a function that we call as soon as we define it. We are able to have a closure for this function so we can create variables that don't conflict with other variables in scope, and we can pass arguments to it. And the arguments that we're going to pass are our module definitions. We're going to have a massive object, and the keys in the object are going to be the IDs of the modules, and the values are going to be the actual executable code for the module. If we have multiple chunks, things get a little more complicated. Each of our chunks is going to be loaded as a script tag. And for our chunks with entry points, we are going to still use immediately invoked function expressions. When our chunks just have dependencies, like the vendor chunks we saw in the previous example, we're going to use the JSON-P chunk format. And when we load these chunks, we're going to put the modules into shared memory. And as soon as all of the dependent modules for a chunk with an entry point are loaded, we can finally execute the entry point for that chunk. Usually, the chunks loaded via script tag are going to be served from some kind of server. Maybe it's the Webpack dev server. Maybe you've got them on a CDN. We're almost ready to dive into hot module reloading, but we need to talk a little more about the Webpack architecture. So when we enter into a Webpack build, we execute something called the Webpack core. And in this core file, we're going to parse our Webpack config, and then once we've got our config, we're going to apply a bunch of defaults to it. And during the process of applying defaults, we're also going to apply plugins. And this process is really important because as of Webpack 4, using the defaults supplied, you can actually generate a valid build. Most of the interesting functionality is implemented as plugins. So these plugins are very important for continuing with the rest of the build. And once we've applied the defaults to our config, we create a compiler and we initiate compilation. As soon as we start initiating our compiler, it's going to start emitting events. And these are where most of the interesting work happens. So most of Webpack's functionality, like the parsing of modules, the generating of source, the generation of the runtimes, is written in plugins that all live within Webpack's source code. So our compiler is going to do a few steps over the source code, then it's going to start emitting events, which trigger plugins, which then emit more events, and we end up branching out into a bunch of different plugins. And the plugins are able to return, and they're able to pass control back up to the previous plugins until eventually we give control back to the compiler and it emits our assets. The problem with this plugin architecture is that it's really difficult to trace what's going on in a Webpack invocation. We're looking at something called the seal function here. This is called after we've generated our intermediate representation, and this is when we do chunk optimization and also emit our assets. And you can see all of these hooks that get called, and each time we call one of these hooks, there's a layer of indirection. So when you want to debug a Webpack build, it's very hard to trace what happens as you go through these hooks, because each time you call a hook, you need to do some kind of string-based find operation to see which plugins are registered for that hook. We're going to look at an actual plugin here. So the interesting bit of this plugin is the class definition. A plugin is just a class with an apply function. A plugin gets passed a compiler instance, and then all of the interesting bits of the plugin need to happen via compiler events. So in this case, our plugin registers for the entry option event. This is the event that gets called when we parse the entry section of our Webpack config. And in this case, the plugin is just going to be looking at the value of that entry and seeing which type of values have been provided so that it knows what we need to do in order to compile this type of entry. So we now know all of the terminology and all of the build steps needed to look at the implementation of hot module reloading. At a high level, we're all familiar with hot module reloading. Something changes on the server. The chunk graph is invalidated if any of the dependencies have changed. The browser is told, hey, you no longer have up-to-date dependencies and you need to load new ones. And finally, our application is able to respond to these new dependencies and update itself in response. So let's see how Webpack actually accomplishes this. So Webpack itself is going to be listening for file system updates, and as soon as our source code changes, we're going to start a new compilation, and this is still happening in Webpack. And we start this new compilation, we undergo the process before, we generate our intermediate representation, and we generate the source code for each of our modules, and finally we emit a post-compile hook. And at this stage, we will have generated source for each of our modules, we'll have broken the modules up into chunks, and crucially, we'll have that manifest for each of our chunks. So we'll have this mapping of module ID to a hash, and we can use this hash to tell if that particular module has been updated. So we look through these updated modules, and if the modules have been updated, the Webpack dev server, which is implemented as a plugin, is going to send a WebSocket event to the browser. We're going to have some code running on the browser that's going to be listening for these events. And as soon as this code running on the browser sees the event that the chunk graph has been invalidated, it's going to send a message to the window. And within each of our chunks, we're going to have a small runtime provided by the HMR plugin that says, hey, these modules are no longer good, we need to load new ones. So when the hot module reloading runtime, or the HMR runtime, realizes that there's new and updated dependencies available, it's going to swap them out. It's going to talk back to the Webpack dev server, it's going to retrieve the new chunks, the new modules, and it's going to retrieve them by injecting a script tag into the page. And once the new dependencies have been loaded, the HMR runtime is going to swap them out. You might be wondering, like in the case of React hot module reloading, at which stage do we actually update our framework data? So if we have a React virtual DOM, when do we update that with new components? This doesn't actually happen in Webpack itself. So if you just use HMR on its own without adding a layer at the application level, you're probably not going to get good results because you will have swapped out your modules for updated ones, but you won't have told your application that it can use these new modules. So in the case of React, we need to provide another layer that listens for these chunk update events, and when we get them, we're going to actually swap out the components in the virtual DOM and trigger a new render. So we've hand-waved away at this point how we get this code to run in the browser, how we listen to these WebSocket events. And the way we manage that is by actually putting a new entry point into our Webpack config when we run the Webpack dev server plugin. So we load our Webpack dev server plugin, it modifies our entry points to add the Webpack dev server client, and then when we build our application, we're going to have this new chunk that's got a Webpack dev server code that's going to be listening to the Webpack dev server WebSocket events, and that's how we're going to do hot module reloading. So what can we take away from this? Well, Webpack is extremely flexible. Using plugins, we can pretty easily hook into any stage in the compilation process without having to understand the Webpack implementation itself. And if we do want to contribute to Webpack, it's very easy to add new functionality without having to understand the existing code, because all we need to do is find the right hook. But if we do need to debug complex problems in compilation or in any other stage, it's very difficult because we need to trace the execution of these hooks throughout a bunch of disconnected plugins. And now we understand hot module reloading. That's it, and I think we've got some time for questions.
Thank you very much, Bill. Anyone interested to ask a question? Yeah.
Amazing breakdown. I just have one very quick and simple question. How many sleepless nights took you to dig down the rabbit hole?
More than I'm willing to admit.
Any other question? Yeah, it was very. Thank you very much, Bill. It was very, very impressive, very interesting. So that's it. That was really interesting. Thank you very much for coming. Thank you very much, Facebook, for hosting us. As I said, we can meet in the pub later. So Red Badger is also organizing a meetup this Thursday. It's called We Love Tech, and it's about accessibility. and we still have some tickets left. So just Google Wheel of Tech London, and you can get some tickets. So thank you very much. See you next month.